And we've begun. So
I will have to submit the attendance for this class. The last, I was gonna see you once a week, so make sure that everybody signs it who's here. Print your last name. We're supposed to have 15. If anybody was, you can make, if you weren't here last week, who just transferred in, let me know, because we had 17 last week, so we had more outgoing. Supposed to have 15, but you usually find out by the end of the second week who's here and who's not. Because we're obligated. This is, normally it's Friday, but since, I'm not, just not a Monday, Wednesday, Friday class. We're doing it this way. Okay, number 2 on the hit parade. Let me take you over to Blackboard. Here, this is the Blackboard for our group. Coming right up. Here we go. So what I added, which I hadn't done before, I added some, first of all, just to show you one of these. These are, we do the skin unit, but I have extra handouts, which you'll see for biochemistry, for this chemistry handout I have. And if I didn't put that in, I'll make sure I put this in for the stuff we're going to discuss today. Basically periodic table stuff and basic science that's coming up. And this is, again, these are, I made these a number of years ago. If you see any references to figures, they're from older editions of different textbooks. But whatever you're working on with tissues and skin and lab, Dr. Robbins, this will help you. We do skin unit here, but we'll do that after cells. So you sort of revisit some of the highlights of skin. And you'll see those documents are there. This just basically I've outlined the chapter. There's a lot of good material on here. It will help you in whatever you're studying. It's good to look through it. So you see it over here. I have skin, I have tissues, and I did this is the outline that would be sort of relevant for today. This biochemistry outline. Really, a lot of the stuff went over. I took that from a micro textbook I was using 20 years ago, offhand. And understand that's where a lot of this comes from. We did basically, more or less, we finished chapter 1. There's not a lot else to say about it. That was there. And I'm not going to be using the Welsh whole chapter 2. I might have even loaded it twice. Probably did. I wasn't sure if I had loaded it before. But we are going to be using this. I probably did load it right. We're going to be using, I'll show you this outline. Come on, Luke, get back to the top. Yeah, I reloaded that twice. I'll get rid of it. So it's this. We're going to be using, this is from a different textbook. And this is the textbook we used previously. I used it because I think that the illustrations are better. And although not on this particular set of PowerPoint, but when we get to the cell and muscles and nerves, they have exceptionally good animations. The animations we can play, you'll have them, you can look at them many times. We're going to be looking at the intricacy of how resting membrane potential, which is critical to understanding how cells work, how muscles work, how nerves work, and then the specifics of muscles and the specific of nerves. All that is really, that's the intense part of the physiology in this course. To me, the anatomy is fairly straightforward in a lot of these areas. It just requires a fair amount of memorization and, and certainly a degree of understanding. But when it comes to understanding the physiology of the cell, the physiology of nerves and muscles, to me, that's the most difficult portion of this particular course. And so I think these animations help. Just, all of these are resources for you. I only you can determine what benefits you and if it's beneficial. Understand that. And I know we end up, because of the way this is formatted, there's a lot here and you're stuck listening to me for the better part of 2.5 hours. Even I'm tired here. I've been talking for 4 hours today. Imagine when I get home, my wife can't stand it. Shut up, you talked all day. And with that editorialization, here it comes. Chemistry coming alive. And I will be flipping out of this. And what I just sent you in an email was a periodic table. We'll get another one ordered. I'll find one that's a little smaller and try to get it put up. And we only really use it for really this section more than anything else. So I have it set up that I could frame on it. It's a science classroom. We put one up in the other one, but I only had one this morning. And so, and because, and because my colleague is teaching his course over there, we can't flip-flop the classroom very easily. But here it comes. So this is all effectively the first, the A PowerPoint, which we're doing effectively today, covers, for all intents and purposes, the basic chemistry. It's a review of chemical stuff. If you're sitting here, you had to have it some way, shape, or form. They had to tell you about protons, electrons, and neutrons. They did. They had to tell you about bonds. They did. But I'm going to try to put them to you so you can understand the relevance it has to us. Why it's so terribly important. I can't tell you how much we call them basic sciences. In any field of endeavor that's a scientific field, and for most of you who are taking this course, you're in it for that. You, when in doubt, you go back to basics. I had a very strong frame in medical school. We did 2 years of basic sciences, make you sick. Hardly anything clinical. And it's, everybody, I want to go see patients and go out on the floor and do this. The basic sciences serve you so well, particularly as the studies get more difficult. And you're the only group I'm telling you this. It's just, it's like building a foundation. If you build it strong, you have something to lean back on. I know it sounds like a bunch of, I would say baloney. You thought I was going to say a bad word. Yeah, bovine feces, cow cookies. As my grandfather used to say, donkey dust. But I wouldn't say that because it's inappropriate for the classroom. Trust me. So that's where this comes from. Okay, to understand it. So we've got to do the basic principles of chemistry my way, which is fun, I hope. So all of that, and then I doubt that it would be this week. It would probably be next week. Maybe we get an intro. Really, the relationship is biological chemistry. We're made out of chemicals, mostly organic chemicals. And all the fancy word organic just means carbon to carbon and carbon to hydrogen bonds. We call covalently bonded. And we're going to go over a little bit of that today, I'm sure. And it basically involves the sharing of electrons. As long as what's so important about that, we store energy in those bonds and we derive energy. When we ingest something, it's full of these covalently or shared electrons. They're seeping with energy. And what we do is we strip them away from their bonds. We suck out the energy and effectively spit them out. The whole idea is taking these electrons that can do a lot of harm because they make things unstable and finding a way to excrete them. But really and a lot of times with that extra energy, if we've ingested too much, which I am prone to do at times, okay, if you have an overabundance of energy, you store it. And so you have to find a way to store that energy. You'll find out if we don't utilize it within about a minute, then our body immediately starts to store excess energy as fat. And we'll go into all of that as we talk about the limited way we can store it as carbohydrates, which effectively are sugars or complicated sugars in this case. And most of the time we end up storing it as fat. Not as necessarily bad. Fat's a great source of energy as long as we cope with it appropriately. Nevertheless, that's sort of the foundation that we're growing here. Simple stuff. And I am not going to, these kind of definitions I'm not going to ask you. Matter, mass and occupies space. Which many times defines our dog, because he doesn't do a whole lot else at times. It's a very nice dog. Okay, and the only difference between that, mass and weight, and I use the term interchangeably, you can too. I'm not going to ask you the difference. The big deal is gravity. Okay, you're up in space and it's weightless. You weigh 125 pounds. You weigh 125 pounds there. But you don't have a scale to step on. And that's really what defines our weight. We have some way of measuring it. So we effectively, gravity, basically, we step on a device somehow in some way, shape, or form, sit on a device, are able to measure it. Mine, I frequently like to kick when it says what it thinks is right and I don't believe to be right. You see, it's like, they always do that. Do you ever notice it? See, as you get older, when you go to the doctor, And the first thing you walk in the office, what do? And then your blood pressure. I get mad about that. Do me a favor, check the blood pressure first, because I'm only going to get very agitated. The old days, they had that scale with, it wasn't digital. You had the little weights, and they put it on the old weight. You step on it, and then they start to, and you see the nurse, whoever's doing, going, I know what that meant. I used to joke with my family doctor, and she was my family doctor for many, many years, our whole family. I walk in and I'd say, hey, Janet, how's it going? I know. Lose weight, stop smoking. Here's your copay. And I'd start to walk. So wait. So here we go. Solid, liquid. I'm not going to ask any of those types of definitions. Unnecessary. We know what they are. It's important to understand that all of those play a role. Our bodies are filled with our blood effectively is liquid. We're made of solids, but gases play oxygen, nitrogen, hydrogen, carbon dioxide, all play a pivotal role, okay, as gaseous elements that we contend with that are there. Yeah, energy is something that doesn't take up that stuff. And the more we use, effectively, the more we have to utilize energy to sort of translate into work. That's all fine and dandy. I use the term, rather than metabolism, I love the term energy transformations, because that's what we do. We're constantly, if we ingest something, food or liquid, and we derive that energy, we suck it out of all those electrons. Couple things, we can either use it directly to do stuff. If we have excess, we're going to store it. Okay, we maybe we're storing it intentionally. Maybe we're building. Maybe you had an injury and you need new cells, or you had to replace a certain amount of bone that may have been injured. All of those kinds of things. That's what our body does all the time. So it's constantly a process of transforming this energy in steps. First, every time taking it out of our foods, it sacrifices some energy. Putting it back into our foods utilizes some energy. Just sign that when you can, please. And so all of that is part of it, this whole idea of energy transformations. So that's something I talked about a little bit when we met last time, with energy transformations. And so and every time we utilize that, unfortunately, every time and the fancy term that we use for it, oh yeah, I know, because last time I know you were yeah, that's okay. It's last time I saw you were, all of these are on, I send you all these YouTubes and all the PowerPoint, so you get all this stuff. I mean, so I'm happy to, if there's something you want me to explain, I'll be glad to do it. It's just that we have so much to cover in a limited period of time. That's there. So, getting back to it. So when we ingest that food or liquid, we pull some energy out of it, we're going to lose some of it as heat. If we're going to take it and build something, we're going to lose something as heat. We're going to take it and spend some of the energy as we transform it to different kinds of energy. We're going to lose some of it. It's the nature. It's one of the fundamental laws of nature. That every time you do a transformation, or with a fancy word that we do is transduction, it's like you're hearing my voice. Okay, it's a combination of mechanical energy, moving your eardrum, some little bones in your ears, okay, moving that wave along in the interior ear, and then basically creating electrical current. And that electrical current makes its way up to this area called the temporal lobe, which I'm sure you've had with Dr. Robbins in lab. And that's where we process it. So we've converted it now from mechanical energy to electrical energy. Now, when the nerves talk to each other, that sound, did he say dog? Did he say cat? Did he say person? That interpretation is nerves conversing. They do that. Nerves don't talk directly by sending electrical signals. When a nerve effectively talks to another nerve, it says a chemical message. Our nerves are electrical, but communicate with other nerves and very often other structures by releasing chemicals. Very famous word that you're going to learn about toward the end of the course called neurotransmitters. And they're right. It's really exceptionally important. It's great that it comes toward the end because you have a pretty good foundation by that time. So all of that is part of it as well. And this particular animation I will skip. It's just this is potential energy. When you pull back the bow, when you release it, it becomes kinetic energy. Stored energy. And this way they're stored, ready to go. It's like anything. If you're pulling back on something like that, you're storing it. So we do that, and when we store energy, we make bonds. How do we store energy? Just the way we get it from materials, we store it in chemical bonds, as you will see. Today will be the introduction to these many different chemical bonds. And then when we release it, it's doing something, so we call it kinetic energy. We're not talking about speed or necessarily meaning motions. Doing something is the best way, I think. And so we can release it. Even if we store it, we can release it afterwards. But again, every time we do that, there's a little expenditure. It's not one-to-one. We're losing a percentage. Maybe small, maybe large percentage. So this is sort of part. In other classes, we were just starting this unit and got through some of it. Hopefully we'll get through the vast majority. So as I was telling you, most of what happens in our body, I would dare say, is chemical energy. You're breaking up bonds or making bonds. And that's really more of a chemical process. Sucking out the energy is a very famous process where you get the energy that you don't have to know, called the Krebs cycle, okay, proton motive force, and all that. But it's useful to have an idea of why those terms are important when you hear the question.
Thank you.
Okay. And electrical energy, is again something that, from charged particles, it's really very important. I mentioned it in passing when we talked about the resting. Every cell in your body has a charge, like a battery. The difference is that not all of those batteries conduct impulses. Only certain cells have that capability. Nerve and muscle cells, particularly. But all your cells have a charge. They're there. And we'll get to that, what we call resting membrane potential. And then mechanical energy is this. Here, your eardrums, they're vibrating, just like a drum, they're making a sound. If they're too stiff, if they're too flexible, they won't make the right sound. If they're too stiff, if you have an ear infection, not only won't they make the right sound, they're going to hurt you. And then we'll even talk a little bit about, it's more physics than anything else. We'll probably briefly touch on that, maybe even a little today. Particularly X-rays and things like that are what we call ionizing radiation. We talk more about it in microbiology, which many of you will end up taking. Okay, or maybe some of you have taken it already. It's one of the ways we sterilize things, for instance. But that's very dangerous stuff. That's why overexposure to X-rays or other types of radiation is bad. They can disrupt cells. Okay, so we'll look at there's different kinds of energies and different ways that they impact us, so to speak, would be the way to describe it. I mean, when you talk about heat, it's the simplest kind. Temperature is very simple. What it is. Most people, definition, temperature is this. Average kinetic means moving around. Energy of particles. But in this room, I don't know, to me it doesn't have a lot. It's kind of normal temperature or whatever. If we would turn off the fan and close the windows, it would get warm. Temperature is measured by how fast. So let's say my sensors are saying, let's just fairly comfortable, let's say 70 degrees arbitrarily, don't know. If I would have this, how rapidly those particles are touching the sensors that we determine temperature. If we close the windows and maybe turn up the heat, those particles move around faster. The faster they move, the more they trigger those sensors. The faster they trigger them, my brain registers that as heat. And then I begin to feel things associated with it. Those changes that occur from me trying to deal with heat, like perspiration. So there's a lot to it. And why it's so valuable, why utilizing heat during these energy transformations, heat basically as a measure of increased temperature speeds up the kinetic energy, how fast they're moving. So all those things that your body does, repairing something, replacing something, making new cells, making new building materials, it goes faster. Up to a point, it's good. If it's excessive, then there's a problem. So a little bit of temperature is good. That's what we call it. Inflammation is your body responding. It's not, if anything, clinically, we would see a patient who has an infection. They get a big cut on their leg. They're a diabetic. We know it's going to get infected. We're trying to treat it. And, you go, if you examine them the next day when they're in the hospital, and go, this thing isn't terribly inflamed. You could lead a blind eye. Oh, that's great. They're healing. Or you could say, because if it's supposed to bleed a lot and it doesn't, that's a clue. If it's supposed to get inflamed and it doesn't, that's a clue. Presence of a thing can be just as informative, and sometimes the absence of a thing. So we look for things. If it's something outside the normal, the question you want to ask is why. Or from a standpoint, if you're a nurse or a healthcare practitioner of any type, that's when you basically say, we got to figure this out, or call it to the attention of somebody whose job is to figure it out. Little stuff like that. And somebody like me who did this stuff for 25 years, and I was teaching about it for 25 years, can kind of give you a clue as to what happens. These are energy conversions. Yeah. Great. So I'll buy the lamp. That's physics. I don't do physics. Don't do plants. I don't do physics. I don't do teeth. That's not in my, I have a contract that says that. Lou does not have to do teeth or physics or plants. So I'll qualify as being unqualified in those. And here's the heat, which we can partially use for energy. So now we get to this thing, the periodic table. So I mean, in an effort to be a full disclosure, I'll show you the one I sent you. Show me the table. There it is. Blew it up a little bit. Periodic table of elements. You've all seen it. It's supposed to be here. Effectively, what it does is it's able to, it's a construct. When you say an element, this is when we talked about with the emerging properties last time. Protons, electrons, and neutrons have no identity of themselves. But when you put them together in a consistent pattern, now you have an identity. We call that an element, all of those symbols are basically a piece of matter that has, the first time it has an emerging property, an identity. It's solid, it's liquid, it's gas, it smells, whatever it is, and it's composed of atoms that are identical. And we just what happens if we break that down? Those elements, the atoms, the atomic particles, they lose their identity because they go back to protons, electrons, and neutrons, which all look the same. There's no way until we assemble, and that's the idea. We utilize the table. Just a couple of things to point out. You don't have to know it because if there's a test, I'll print this up and give everybody. I'm not asking you to memorize it. It is not chemistry class. Please. Majored in chemistry, 52 years, but a long time ago in a galaxy far away. Here's hydrogen. That's the atomic number. We'll see, number of protons. That's the atomic number. Since it doesn't have any neutrons, normally the mass is also 1. Notice it's 1.008. It's not from the one electron. The electrons have negligible weight. Where did that come from? All of these are like that. Carbon. It's over here. Hello. There it is. Carbon's great. We're carbon life forms. Okay. That's the basis. That's the major. Carbon is maybe not the most, but it's the most important in the sense that that's really the basis of what organics are made of. Compounds made of covalent carbon, by definition. Carbon is 6 and 6. 6 protons, number. atomic mass or weight in terms interchangeably at 12. But hey, it's 12.011. Okay? You will find out all of these members of this table. Reason that these atomic or mass or atomic weight numbers are not exactly the number of protons and neutrons, if indeed you're supposed to have them. There's variation in nature. The variance is the neutrons. We know this.
Yeah. Yes.
I commented last time on carbon 14.
Yeah.
Mentioned that last time, carbon 14. Carbon 14 has basically, did we say that or not? I have 3 classes, 4 classes. Yes? Okay. Those of you who are awake. Did we say carbon 14 last time? Good. Carbon 14 has 2 extra neutrons. What happens is it destabilizes the nucleus, and what it begins to emit particles to sort of lighten it, because it's an unstable nucleus. Okay, unstable nucleus, basically it's emitting a kind of radioactive material. It's a fancy name that we'll get to called a radioactive isotope. Fortunately, it's tiny amounts and they really have no impact on us, thankfully. But it allows us to do carbon dating because we take things that we have a known date that are made out of carbon that's verifiable for over hundreds, if not thousands of years, and we can extrapolate in either direction because we have a formula. It's kind of like the same formula you and I would use to figure out a car payment. If we bought a new car, we're making payments, or a used car, or a mortgage. Basically, you use something called logarithms. So if you're familiar with all with those kinds of things, mathematical, our actuary science department here, which is great, that they're all into that stuff. Moving on, back to the PowerPoint. We'll be back. Didn't leave yet. Big 4. Carbon, hydrogen, nitrogen, oxygen. 96% of us, C, H, O, and N. So we call those the major elements. The next 9, and really the only ones that maybe to be familiar with immediately, are calcium and phosphorus. In our kind of cells, for us, animal cells, the next 2 are calcium and phosphorus, in that order, after C, H, O. As you see in bacteria, totally different, single-celled entity is actually sulfur and phosphorus. Obviously, we're not the same, but calcium undoubtedly has to do with bones, which are giant storage of calcium. So if you remember those, you're pretty good. And then everything else, right? Anything that's in this area, the less than 0.01%, we call those trace elements because there's just a trace. It doesn't make them unimportant. Indeed, with the beauty of trace elements, we just require a tiny amount. If we don't have that amount, it can cause significant problems. You'll see when we learn about the thyroid, we use just a pinch of iodine, which is a salt. A pinch, a tiny amount. And we get it, by the way, because we get it in any kind of table salt or foods that you would purchase, whether it's canned or frozen or foods that you buy, pre-prepared foods. They're all going to have enough iodine in that easy to avoid thyroid problems. The major ones. Tiny amount of iron. Without that tiny amount of iron, we can't make hemoglobin, and that allows our blood to carry oxygen. Tiny amount. Biggest problem we have when people don't have enough functional red blood cells, meaning a lack of hemoglobin, iron deficiency. We have a fancy name, iron deficiency anemia. You don't want it. So talk about tired. That's tired. So, and the periodic table is all about these. But we look at it individually as the atoms, and it's aptly stated, unique building blocks. They're all different. It's just different combinations of those 3 components. Okay, smallest particle, so an atom would have the same properties as an element, yes. Okay, and what I like about this PowerPoint as opposed to the other one even though we're going to go back and look at the Welsh Hull textbook. The Welsh Hull textbook is good. It's a little bit, it's sort of an in-between. I think the major reason is if you did get that textbook, there's a software package that really helps with anatomy. I don't know if Dr. Robbins is using it or not, but there's some really good aspects of the software for the anatomy. And you can use those, and graphically it's very distinctive for something that's, and we study everything two-dimensional, but it's really supposed to be very good. I don't particularly feel it needs to have a little bit more to it. Sometimes it does. One of the things it didn't really talk about, they talk about chemical properties. Physical properties are so important, and we neglect them. I'll agree that it's mostly chemical stuff that impacts us, but physical stuff impacts us too. And we have to be aware of that as well. So again, pretty straightforward. I'm shocked that you didn't have all this stuff before. If you didn't, I mean, that's really, then wherever your program you took, assuming that it was in high school or maybe another junior college or however, they missed the boat. I mean, to be critical, they did. So again, all the names, you don't have to know the Latin stuff. It comes in handy. Like the word natri, that prefix means sodium. That's used. The K, I don't think for potassium. The kalium, I've never seen. Usually we talk about, someone has we want to look at their K. And you just have to know it's potassium. And typically for sodium, in a hospital sense, that's what they'll talk about. And there you are. These are just crunching the numbers C, H, O, and N that are there. And you can see that roughly adds up. And you can see how much it is to the body mass. I mean, oxygen is a giant amount because not only do you have gaseous oxygen, we have our bodies are 75 to 80% water by weight. So you might imagine a lot. I mean, it's a lot of water. And water is heavy. You got to lift a couple of cans of water. That's no picnic. Things like that. It's like when you come, like we're always the ones that end up going like Costco or Sam's because we're having to get together. They say, "Oh, would you guys pick up the water? We need like the 40 little, the ones, and then the sparkling ones." I mean, my wife and I are both lifting those together. Thankfully, she's younger than I am and fitter than I am. Here's the calcium and phosphorus. And now we work our way down here. Now we're getting down to those trace elements, but they're really important. As you can see, they play a role in a lot of different things. Hemoglobin and thyroid. Here, metabolic reactions. I don't know if the term cofactor is probably accurate. Okay, I mean, all of these things, there's so much that goes on. And you'll see as we get on with this and in the second half of the course in spring, okay, you'll hear more because that gets more into more in depth into the physiological phenomena that are occurring. And so here are the trace elements. And again, I'm not going to sit there and give you which one of these is a trace element and put it in selenium, something like that. But, the ones you deal with iron and iodine, that's pretty straightforward stuff. Standard stuff, everybody had it, I hope. Protons. I don't know what a mass unit is. I don't know how much you would measure it in picograms or whatever it is. Okay, the same thing with a positive charge. It's 1 unit of charge. I had no idea how many nanovolts that might be. So we just arbitrarily have assigned a mass unit and a charge. So it's 1 and 1. You had this before. I'm not going to ask you any more about than that. Protons have mass and a charge. Neutrons have the mass and no charge. Electrons have a base. They have mass, but it's virtually unmeasurable. That's why it does. When I showed you the periodic table, it does not account to that number. Hydrogen's 1 electron didn't make it go more than 1. helium's 4 electrons didn't make it go more than 4. It just did. 2 electrons didn't make it go more than 4. Okay. And so, atoms by definition are neutral. They have equal numbers, and you're going to see what happens. We rarely see atoms in their atomic state. They have undergone some change. They've either bonded with something else, or they have either lost or gained those electrons to become more stable or more functional. That's really part of this discussion. This is something you may have had. It's not critical. The hard thing, I think, for entry-level students in these kinds of life sciences is to understand everything I'll show you here. They're talking about the difference between what they call the orbital model, planetary model with orbits and shading and blah, blah, blah. That basically everything that I present you, all your courses, is two-dimensional. That's one thing you'll like, I think, about those animations. They're so well put together that you really can almost sense the three-dimensionality. They're just wonderfully done. That's the only way I can say it. Is for me to try to express something and have you understand that we're looking at it on a flat surface. There's nothing like, bodies are not like that. Molecules have different shapes, and shape is everything. Particularly when you get to proteins, their shape determines a lot of what they do. And that's what I'll be endeavoring to show you. I won't get to it today, but we'll probably get to it next week. So here, maybe you got this, in school. Well, there's 2 because this was the way they used to treat it. They used to teach you. You can see, they used to tell you, well, here's helium. And helium has 2 protons, so I'll put 2 plus charges. It's got a couple of neutrons. We're going to put those in. And then it's got this pair of electrons. You got an electron here and an electron here. Because electrons in pairs are stable. That's the way they used to teach you. It's really not that way. What's unique about the first two items, hydrogen and helium, in the periodic table. It's like I wrote, you can see them up there on the wall, and I didn't have a periodic table. Hydrogen and helium that are up there, they only have 2 electrons in their outermost orbital. So that's correct, but they're not necessarily on opposite sides of one another, and they're certainly not together. The reason that is a useful number is it means that they are flying around that nucleus evenly distributed at any one time. It's not like 2 are sitting over here one time and 2 are here, because that would create charge. That would create an asymmetrical distribution. It's just not regular. So they're evenly distributed out, so it's a nice neutral cloud, if you will. That's why I like the cloud theory a little bit better. But this is information. I'll have to ask you the benefits of cloud theory versus orbital theory. This is not a Chem 1. If indeed they still do that. The idea of the cloud is that because this outermost orbital is filled, and everything about their chemical properties is about the outermost orbital. Helium. Okay? Outermost orbital is complete. It only has 2 spaces, and they're occupied. And when you go back and look periodic table-wise, that means that these are chemically stable. So if you go back and flip over again, I gotta keep doing this, to the periodic table, and you look at where helium is, all of those in that far corner, as you look at it to the right-hand side, those are what we call ideal or Nobel, and they're all gases. Helium, neon, argon, krypton, xenon, radon, whatever that is. That was made artificial. Their physical properties are different. We know about helium, lighter than air, right? Hydrogen, lighter than air. What's the difference between hydrogen and helium? Did we do this on the side? Did we talk about the Hindenburg? Didn't talk about the Hindenburg? Does anybody know what the Hindenburg was? Historically insignificant. might be. You wonder why somebody did, but it's not enough. It's me wondering, why did they know about this stuff? But in education differs. In 1937, no, I was not around. My mom was 19, and in either Lakewood or Lakehurst, New Jersey, there was such a large explosion of a dirigible, EAB, you guys call it, a large blip. In those days called a dirigible, that as it came in and began to be docked, so they secure the ropes, it exploded. It was from Germany. Understand we were at World War II was coming, everybody knew it. There's a lot of very interesting fiction about whether or not there were spies on it, whether or not they were carrying plans for atomic energy, which is 100 years old. And I love to read those. Long story short, those dirigibles then were filled with hydrogen, with a physical property of being explosive. Helium is not. But they wouldn't be selling helium to you for the little kid's birthday party. But for those of us who have fun with it, helium, talk with the high-speaking voice. Yes, we did. 3 kids. That stuff's got expensive. You used to get the cylinder, you go to like wherever, Party City, not Party City. But that's historically significant. My mom, who was 19 at the time, 50 miles away, she told me the sky lit up. There's when I was born in 1988. Because we all saw that from Newark, New Jersey, which is 50 miles, it's about 20 miles from New York City. Where I grew up. That's where she lived for the first 4 years of her life. Okay? That's the distinction. So even though it's inert, neon, we have all LED lights today. You go to Vegas, you go to Broadway, in old days it was neon lights. They knew it would glow, and whatever colored glass you put it in, it would light up. Here in the textbook, they'll show you that radon occurs sometimes as an element that comes from uranium as it decomposes. Not that we're rich with uranium here, but when you dig, you're going to expose some very radon. This whole area where we reside here, or if you don't reside here, if you're like me, I've been residing in Pittsburgh here for quite a while, for years, and around this region. But it's all been strip mined. They basically had big steam shovels and tore the earth, got whatever coal, mostly they could get out of it, other minerals, and filled it back in. Houses were built on top of this. When we sold our house, which is O'Hara Township, if you don't know where that is, think about where the zoo is in Pittsburgh, go across the river, look on the hillside there. It became mandatory, you had to monitor radon levels in our basement. So we had to put a radon detector, which we hadn't had in there. We were selling the house and found that there was measurable radon. It can cause lung cancer. So what we had to do was one of 2 things. We could either take the money off the price of the house, which is what we did. People were coming in there. Or we had to perform radon mitigation, which was, we had to put like an exhaust fan from the ceiling in the basement with piping that went outside, like by the chimney. And then the radon blew out into the environment. Is that good? I don't know, but it got it out of the house. It's sort of counterintuitive. So basically, in those days, it was $1,000, took $1,000 off the asking price of the house. Fine, you guys decide. I wouldn't know something different. It's 25 years ago. That's something, and anybody who lives here, probably if you're going to live here, if you get a home of your own, I'd put a radon detector in just to make sure. See how severe it was and did I have to do anything? You probably would know about it too much. That, again, it's still more or less a physical, even though probably it's impactful as a chemical part, I would still classify it as physical. It's just interesting to me. And that's why I endeavor to show you these things. And this is the same stuff. It's not because I like you. I actually did the same thing with the other classes. Today's the 4th time I'm doing this. And I could just sort of break it up again. But inevitably, it's different. So here, this is the big deal. You all should know what an atomic number. the number of protons. Atomic weight or mass, I'll use one or the other, not both. Okay? Protons and neutrons. The electrons we don't count. The big deal, like carbon-14, is an isotope. ISO, save. We use ISO a lot. ISO. Tope to me means type. And by definition, this is something that is the same chemically, okay, but has different physical properties because of the additional neutrons. It's still a hydrogen, but it's not when it becomes this. So you'll see. So here, hydrogen. So look at these three. Now, again, hydrogen and helium have only a maximum of 2 electrons. That outermost orbital, you can see here's the inner orbital. The inner orbital has a maximum of 2. So hydrogen and helium are somewhat unique. And I'll show you about hydrogen in a second. Once you get to everything else that we're going to really look at, things like lithium, things like sodium and potassium, chloride, fluoride, iodine, all of those, oxygen, phosphorus, nitrogen, all of those, that outermost orbital has 8. It's called the octet rule. You may have heard of it before, probably did. That's 8 electrons. So lithium, I just don't see, lithium is technically an alkali metal. You'd never see it because it has this 1 electron and there's a maximum of 8. You have a choice. You either lose 1 or gain 7. Trust me, it's going to lose 1 like crazy. Call that ionizing. When you lose or gain electrons, it's called an ion. It's a charged particle. If you lose electrons, it becomes positive. So how do we see it if it loses that 1 electron? We see lithium plus 1 charge. Calcium, the building block of our bones, has 2 in an orbital of 8. So rather than, it could conceivably gain the 6. It's interesting. Maybe not the best example, but we always see calcium with a plus 2. It loses those 2. Lithium's been around forever. If you did not know it, lithium chloride was common form, was the early and still a fairly effective treatment for treating depression, major depression. The problem is side effects. So, I mean, you have to monitor blood levels. For those of you going into with patient care and you're looking at their meds, you'll see something. You just will. Because it is, a lot of times it works better than some of the other stuff. Just because everything has side effects, you always have to look at all those things. So that's the idea. That outermost orbital is sometimes called the valence, VALENCE orbital. The valence orbital is really where the chemical properties come from. And that's the beauty of the periodic table. I'll flip out once more to show you. That's what they make columns. That's why it's so important when you're in like chemistry class. So all of these, fluorine, chlorine, bromine, iodine, they all have similar properties. They all, as you will see, all they want to do is gain an electron. They got 7 of the 8. That's the good news. They're called halogens, HALOGENS. Pretty simple category. Big problem, poisonous. But halogens in something, poisonous. Sometimes we do it intentionally in small amounts, like we have fluoride in our water. Why? Because it will impact the amount of cavity-producing bacteria. And again, I think as time has gone on, it's become more of an issue whether or not to fluoridate the water and things like that. I don't know enough about that are there. And on the flip side of that, all of these guys, sodium and potassium, this is rubidium, this is cesium, but the sodium and potassium are the ones that, believe me, biological science, those are the ones you have to know the most about. They lose, just like lithium, they're an alkali metal. You just don't see sodium in its elemental state or atomic state. We had it in high school. Back in the day, before they had a lot of restrictions on things, it's an explosive metal. If we had it in a glass jar that was sealed and covered in kerosene, it looked like a big piece of chalk, like sidewalk chalk. Kind of grayish because it was buried in the kerosene. Like I remember that the chemistry teacher We reach in there with some, like a long tweezer, get a teeny tiny piece out, and put it, we were well distance, in a beaker of water, and watch it go boom. It's an explosive metal. If you let it expose to the air, with moisture in the air, or to water, it explodes right away. What happens is all the sodium we already see, it's already ionized. They've done this before. It's just like magically, we just don't see it. It's already gone through the ionization. Chlorine, on the other hand, is a poison gas. When you hear about train derailments, the thing you worry about, chlorine. A lot of times when they derail, some of the materials they're carrying will be a combination where chlorine gas will be eliminated. In a submarine, particularly with the submarine battery and seawater, bad mix releases chlorine gas, one of the things that kills sailors and submarine fatalities. I'm good with naval stuff. My eldest is an officer, is a career officer in the Navy. He only gives orders. I know how to respond. Yes, sir. And interestingly, if you're familiar down with the Science Center, you got to start really when my ex, who was working in the Science Center, got him a job helping, guiding people with some other people on the submarine museum. And he went and interviewed the original captain of that submarine in Annapolis, right before when he was still alive. This was about 2000. So we did a senior project on that for school. Nevertheless, that's kind of giving you an idea. So when we talk about salt, it's a combination of an explosive metal and a poison gas. We don't see chlorine gas. It's already ionized into chloride, Cl with a minus sign. So you're going to see that as well. Okay, so moving back to the PowerPoint. I know I'm jumping around, but I find this is a good way for me. I don't want to confuse you, but I'm trying to give you the big picture. That's the one good thing. I know it's having enough stuff to listen to me. And you're allowed to ask questions. Shh. Okay. I mean, if you're in, I tell my wife, I have no idea what this sea of laptops and pads, what you could be looking at or watching. I'm hoping that it's pertinent. It's okay. We didn't have that luxury at our age. I mean, I would have been watching something more fun. He's recording it anyway, all this. It's okay. I can take the hit. So I'm not going to do subscripts and superscripts and stuff like that. I'm not going to do it. This is the isotope nugget. These variations. Again, just like carbon-14, when we put extra neutrons in, most of the time it doesn't make a difference. Okay, the chemical properties are the same, but sometimes it will destabilize that nucleus, and an unstable nucleus will begin to try to stabilize itself by releasing what we call subatomic particles. We don't have to know about alpha and beta particles and stuff like that. Okay, that's more for a physics course. What it means is that's radiation, and it has benefits. We use these radioactive isotopes all the time. Even when I was in practice, and even when I was a student, a lot of the students that come through here to go into nuclear medicine or related fields, basically nuclear medicine means the study and the application of these radioactive things in small amounts, like iodine. We use iodine 131. Effectively, we label the iodine. We can see if the thyroid's working, and if the thyroid has a cancer, we can treat it with that, because effectively it is a poison. There's a chemical called technetium, and we use what's called technetium-99. It's a specialized metal, but what happens, the way we make the technetium, it's very easy to bond it to your bloodstream. And we can trace where blood flows and where it concentrates. So if you're having a bone scan to see if someone has a bone tumor or bone infection, basically it'll make it light up. You can use a scanner. Think of it as something, it acts kind of like a Geiger counter, but it's a scanner that will promote a body image, and we can look at the very areas. So brain scans, bone scans, liver spleen scans. We use these all of the time, and there are many, many more applications that we can advance. if you, most people, myself included, when I've had to have a CT scan done, they inject you with a contrast material that emits these particles, and in the process of doing the serial x-rays, which are what CT scan is, they're getting a picture inside what they call contrast material. I mean, if you've never had it done, and I've had it on a couple of occasions, when they inject you, you feel like a toaster oven. Let me tell you, all of a sudden it's like everything from your fingertips to your toes or just go hot for about a couple of minutes. It goes away. And I had one done, I would dare say, fairly recently, when I had a surgical procedure done a couple of years ago. It just, my surgeon said, "Hey, we got to get this done before." Okay. Here's an example. Now, none of these are radioactive, but they're important. Historically important. There he goes again with history stuff. Hydrogen, when you add extra neutrons, it's called deuterium. If you add 2, it's called tritium. I guess for 3 being weight, effectively. There's such tiny amounts, as you might remember. Hydrogen was like 1.0001. So there's very limited amounts. Why do we talk about this? It's historically important, and perhaps it's even still used today. And one of my students asked me to look that up in Biol, and that's deuterium. We use it all the time. One of the things, the foundation of what we call MRIs today, magnetic resonance, when we did it in the chemistry lab, we were measuring hydrogen ions. What's a hydrogen? So hydrogen is basically a proton, just make a fun, no neutrons usually, and 1 electron. Maybe not 50-50, but it does one of 2 things. It either joins up with another hydrogen and you form a bond, and you get hydrogen gas, the aforementioned explosive of lighter than air, or it ionizes, which means all you have is the proton. Now we draw H+. That's a hydrogen ion. And what's meant to ionize in this case is that we have an electron floating about. That's only really 2 ways we typically find hydrogen. Most of the time, hydrogen bonds covalently. That's what this is. A lot of times it's with carbons. We will see here. Probably after we take a break, I would figure. So effectively, a hydrogen ion, everybody, if it loses this, all you're left with is a proton. So another name for H with a plus sign is a proton. Hydrogen ion equals a proton equals a hydrogen. When you hear about the proton motor force, that's how we generate ATP, our energy resource. It comes from hydrogen ions moving. We have all those hydrogen ions. We have a variety of electrons. And what effectively we do is this. Oxygen, which we need to make the force work, the reason is we've got to have a parking place for electrons, and we've sucked the energy out. So oxygen basically has 6 electrons in its outermost orbit. It sucks up 2 of those. So most of the time we see oxygen either 2 oxygens bonded together, or we see oxygen with a -2 charge. It's gathered 2 electrons. We take that oxygen with a -2, because really what its job in life is a parking place for all those electrons we suck the energy out. And we take 2 of the protons from the force, which works for the same thing in the mitochondria, and look what we get. Water. Love that. Waste product. And that's the beauty of our system. We take the carbons and we bond them with oxygen more effectively. There's a long way we do that. For carbon dioxide gas, the waste product we exhale. And water, which we get rid of a lot of different ways. Urinate out, perspire, we exhale some water vapor. Easy to get rid of, and relatively speaking, non-toxic. What happens if you took regular water, H2O, and chemically, what you can do, replace it with deuterium. We have D2O, but we get fancy and call it deuterated water. It's a very important substance. It's all about really what it does. It doesn't change the chemical properties, but the physical properties. So if those hydrogens are now deuteriums with an extra neutron, what does it mean? What has happened to those hydrogens? Their chemical properties hasn't changed. What physical property changed? If you add something that has mass but no charge. If you add mass to anything. That horrible thing that I step on in the morning that I don't want to look at half the time. And the reason pardon me, I know no visualization. I try to, but I go to the doctor's office. I am not shy. I take off my shoes. I take off my belt. I take out the wallet. I take out my keys. I take out everything. Why? Because all of it adds what? Weight. So if you add protons to regular water, what kind of water do you have? Chubby water? What kind of water? Heavy water. He ain't heavy, it's water. There was a song called He Ain't Heavy, He's My Brother, back in the day. Heavy water. Heavy water was historically, and it may still use it, when you do atomic energy, it generates immense amounts of heat. The way you dissipate the heat, or the way you use it, is to create steam. Okay, if you use regular water, it's so much heat that the water will evaporate because it moves it around entirely too fast. If you have heavy water, it moves it around more slowly, and it's more efficient at dealing with the increased heat that's generated. Heavy water was at the store. Heavy water became relevant in the late 1930s as both sides, the Axis and the Allies, were trying to develop atomic weapons. We traced the Germans, the Nazis had taken over Norway. Norway is where the plant was to make heavy water. Between their resistance fighters and our spies, at great risk and sometimes risking their own or losing their own lives, they got information of where that heavy water was being delivered to in Germany, where the plant was. Our bombers got the message, and boom, we basically truncated their atomic platform. They had already developed functional V-2 rockets, the first intercontinental ballistic missiles. They weren't first intercontinental, but they were going to attack England with them and launch some. Imagine them with a nuclear warhead or an atomic warhead. So that's where they were relevant. Now, whether they still use that today in nuclear plants, I do not know, but I can find that. So I'm trying to give you the relevance of these things. We use it a lot in chemistry, because in chemistry, the MRI machine, the precursor, we couldn't have protons, so we had to substitute a different weight, and that's where the deuterium came in. So the radioisotopes, these are the different things, different element, radioactivity, etc., etc. My wife asks me the silliest question sometimes. I'll get her at the break. And so we call that radioactivity, and the scanners, we covered that. We use research, diagnosis of disease. We use it. You see, I forget what the thing is they're advertising on TV, but you see it in shows. They're talking about something they implant. Basically, I think it's for prostate cancer. They've used radium implants for prostate cancer for forever. They're supposed to be giving us small amounts of radiation. It's not. Understand, if you listen closely to all of those ads for different kinds of medicines, at the very end, when they talk real fast, that's the disclaimer. If you listen to that closely or read it, you'd be afraid to use anything. Because they're basically subjecting you to radiation. For years, that was the state of the art. Thankfully, things are improving over time. There's the radon one. And then we talk about molecules. Molecules are just that. If we have bond two atoms together, they're a molecule. That's the global term. That's the big term. If they happen to be the same, they're molecules. If they're different, they're compounds. So it's a specific molecule. It's a subset of the word molecule. And so here's the perfect example. This is called a hexose. We'll get to that when we look at biochemicals. Hex, 6, as you can see. Os means sugar. So this is a 6 carbon sugar. And those are in the classification of what we call carbohydrates. Carbon and water in equal parts. That's what that is. You multiply by 6, you have 6 carbons, 6 waters. 6 H2O, H2O is going to be H12O6. That's what means by carbohydrates, equal parts carbon. And that's why basically the way we do energy transformations is either things come as carbohydrates or we make them into variants of carbohydrates to process them. So they all kind of lose. The simplest carbohydrate that we use is glucose. And so we try to convert them or find ways to basically insert them into how we're utilizing glucose. So again, hydrogen and oxygen are a little bit different. Okay, they're, if you will, true molecules. I don't know if I'd use that term. I'd just say molecules. It's very rare that we find something in a pure state. Even the air you breathe is a mixture. It's mostly 80% nitrogen, roughly, 20% oxygen, and some other trace gases that are there. And there's particles in there and things like that. And effectively, it's almost like a solution. Dissolved gases or a mixture of gases are like a solution. Solutions are very specific. And we're going to look at colloids and suspensions. And it's a good graphic. You probably all sat in a chemistry class and they took a beaker of water and put some kind of dye in it and you watched the dye diffuse. So let's say if it's a blue dye, like some kind of ink or methylene blue, you put a drop in and boom, all of a sudden you had, time, but you could still see through it. The beauty of that is the particles are surrounded by water molecules and don't obstruct the light. Okay, the light can go directly through it. That's what makes it a solution. We're filled with solutions. Part of our inside the cell is a solution. Our plasma, when you'll see this portion of the blood, if you take a tube of blood and let it and just sit there, it will settle. Gravity will take the heavier elements down, like red cells, called packed red cells because they pack down. White cells and platelets are on top. They're a little lighter. To accelerate the process, we spin it. That's what the blood bank does. They take the blood that you or I might donate, they spin it down, and they extract the part that they're going to use. If they're going to use plasma, they'll take it out there. If they're going to use platelets or white cells, they'll take it out there. And if they're going to use red cells, they'll take it out. It's not all red cells. There's enough liquid in there to make it into a more or less liquid phase. The plasma, even though it has somewhat of a straw color, you still see through because everything is dissolved. And it's a milieu. It's got a bunch of stuff. It's got proteins that are dissolved, salts, and sugars, and other chemicals that are all dissolved. Colloid is different. Interestingly, your blood also acts as a colloid. And that's one of the reasons you can't see through the blood. If you take a tube of blood like that, there's no way you can look through it. Milk is a colloid. It's probably a better example. Milk has a lot of protein, has a lot of fats, it has some carbohydrates in it. It's a good mixture. Mixture is maybe the wrong term, but a composition of something. And what happens? Have you ever seen what happens when milk spoils? Like if you've seen it in a clear, even if you have it like in a carton, it gets kind of lumpy. And you kind of go, ugh. Or you pour some of it into coffee and all of a sudden you see clumps and you go, yup, bad. If you took it and poured it out into like a Pyrex, 2-cup or 4-cup thing, you would see it. Those clumps are proteins that have denatured, is the fancy word. They've changed. What proteins do is they hold water to them. That's what a colloid does. It has a pull holding water to it. When it separates, what you would see the proteins, because they're heavier, fall to the bottom, and the liquid that sits above it would be somewhat clear. That's what happens when you make cheese. Okay? You make cheese, you take basically milk, sometimes different kinds of milk, and you heat it because that accelerates the process, and you put something in there that makes it, you can put something as simple as lemon juice. That causes it to separate. Famous term for that, you've heard this one, curds and whey. Curds, whey, muffet, tuffet, spider, beside. You heard that one, didn't you? Little Miss Muffet sat in a tuffet. That's her. She's eating curds and whey. Doesn't sound that appetizing to me. Spoiled milk. Blech. Now, if you're in England and you're having strawberries and cream, it's like sour cream, clotted cream. So what they do with those curds, they take them and put them into a form, and you make cheese out of it. Okay, and it's the term fromage, cheese. The whey still has protein in it. You cook it again, you heat it again, and do the same thing. That's called recooked. Another name for that is ricotta. Recooked whey, which by law you have to do in Italy. Okay, whoever can tell, there's more stuff in there. You could use it. So you can make homemade ricotta or make homemade cheese. I've done that when you make, it's farmer's cheese. So it's, continue. Indian cuisine. Oh, here's good stuff. Nevertheless, that's what happened. So colloid and jello is a good example because you can't shine the light through it. It won't go all the way through. It has enough solid stuff that the light scatters about it. It doesn't go through it. Indeed, the inside of our cells is a combination of solution and colloid. They call it sol gel, and it varies. When it's doing one thing, it might be a solution, and does other thing, it may become more gelatin-like. So we call it a sol gel. Combination of both. And blood, for that matter, as well as being a colloid, okay, is also a suspension. Suspension just means stuff's floating around and it's moving. As long as it's moving, it stays suspended. It's like salad dressing that you get. So if you get salad dressing, not the creamy kind, but like regular salad dressing, you make it yourself, what do you have to do? Shake it. That resuspends it. When you leave it alone, it settles out. It's kind of like the gravy at Thanksgiving. And you put that into something, and all of a sudden the fat's at the top. You can skim it off if you want to. But what fun would that be if you cook it? Food moment. We're not that far away from Thanksgiving. Remember that. So solutions, homogeneous, so you convey the particles are evenly distributed. Solvent, and these are important terms going forward. We don't use the terms water and stuff dissolved in the water. Effectively, that's what they are. The universal solvent, the stuff that everything is dissolved in, is water. So when we look at, and we're going to look at ratios of solute to solvent, or the other way around. Solutes are anything dissolved in the water, let's say your bloodstream, in your plasma, or inside the cell, or inside the tissues. It's a constant number you will see. And there's all sorts of it. So when they talk about blood sugar specifically, glucose is what's dissolved, but there's more stuff. And it's dissolved in the blood, which is mostly water in the case of plasma, and that is a solvent. So they're important terms because it's stuff that you're going to come in contact with. Again, you could have various things in solution, salts, sugars, gases. And this is the last part. In science, you will not have to. Notice this stuff. Do not get excited. They have molarity. You're not going to have to know that. I don't want you, nor molarity nor molality. You will not have to know that. Everybody knows somebody who's a diabetic. So if I get my sugar last time, I think was 95. That may be even a little lower. Okay, what does that mean? 95 milligrams per second. That means there's 95 milligrams of glucose per 100 milliliters of my blood. That is, we use percent in biological science. In chemistry, they use molar or molar. One has to do with volume, one has to do with weight. We're not going to get into it. If someone is anemic, I talked about anemia before, their red count might be 11. That's 11 is 11 grams percent. So it's 11 grams of hemoglobin per 100 milliliters of blood. So we use percents. That's what you use in biological science. That's what you use in clinical science. So and it's like the same. Why I'm making a big deal out of it. Some of them are grams, some are milligrams. It behooves you to know that. If not now, down the road, particularly if you're going into a clinical field, it's like they told you in first grade: apples and oranges. They're not equivalent. Okay? That kind of thing. So that's how it is. We call it deciliter is a fancy term for 100 milliliters. So if you did, you should be familiar with that. Example, normal fasting blood glucose levels, yeah, I'll buy 80 milligrams per deciliter. But milligram percent is an easy way to say it. We're not going to do that. Do remember this bad boy, at least going forward, to understand how immense that is. Avogadro's number. Water. If you take a half an ounce of water, there are 6.0 with 23 zeros after it. That's a heck of a lot of zeros. Molecules of water. How's that? That tells you molecules are super tiny. So and we're going to use that when we talk about pH in a little bit. Okay, and again, colloids, another term, emulsions. And so a lot of things, not only can't you see them, are they cloudy or milky, okay, but the best way to describe some of them will stay as colloids, and some, when you have a true suspension, okay, beg your pardon, we have a true emulsion, think mayonnaise. Okay. It's designed with something special so the stuff doesn't settle out. If you have a suspension, like I said, with the salad dressing or the gravy, you'll separate. If you add something like to mayonnaise, they typically add, and you don't have to know this, it's a product called lecithin that you find in egg yolks or you find in mustard. And in creamy salad dressings, you generally have those kinds of things. Or in mayonnaise, you have egg yolks typically. So if you make your own creamy salad, it's easy to make. Like that. So that, you can read through that, and yeah, just take a break. So let's come back at 4:30.
Alrighty.
All right. We are going to resume shortly. So when you get the recording, just so you can skip over this 10, 12 minutes. If you choose to review it, that's what you do. Because I didn't bother to, I probably could have turned it off and turned it back on, but easy enough. And so as you can see, I'm sending them with embedded YouTubes. That's the way I'm sending these things. That seems to work the best. Most of the students tell me, if you have trouble opening them, let me know. I can get IT to address the problem. So without further ado, let us return. Okay, and this is sort of where we left off. And a lot of this is just, again, it's common stuff, but it's starting to explain the distinction between these different types of bonds. We're good? It's all right. I can take the hit. Nobody listens to me in my house anymore. It's all right. Moving on. Okay. To me, this is not a big deal. Yeah, stuff like that, mixture, we do that all the time. We take stuff out of mixtures. There's nothing unusual about that. Probably filtration as much as anything else with particles are there. It's not a big deal. And when they talk about heterogeneous versus homogeneous, they are basically whether it's one part, is it just sodium, or is it just sodium and chloride, or is it a mixture of different salts or salts and sugars? That's really what that means. It's not a big deal, okay, comparatively. When you talk like a compound, if it's specifically sodium chloride, I mean, even if you get, for instance, if you get table salt, most of the time it's not just sodium chloride. That's unusual, okay, to get pure sodium chloride. When you get, I don't know what salt you use at your house. If you're using salt that you typically get like a Walmart or Giant Eagle, and it says iodized salt, that's a combination of sodium chloride and potassium iodide, because that's where we get the iodide. That's how you get quote unquote iodized salt. And a lot of it is. You won't OD on the iodide. It just makes sure that you don't have a limited amount. If you like, well, we use that Himalayan pink salt. Some people like sea salt. And all the different salts have different mixtures, as you will see, what we call salts. We'll get to that, just to give you an idea. So, I mean, homogeneous is a little unusual. Most mixtures that we'll encounter are a lot of stuff heterogeneous. So, bonds, by definition, are chemical relationships. And indeed, they're based on the periodic table. And again, it's whether or not in that outermost orbital, whether they want to pick up electrons or donate electrons. And you're going to see the most interesting one by far is what we're made of. It's sitting there, wrong thing. Right in the middle of that periodic table, assuming I can find it, is carbon. And the fact that you're going to see that it's designed, elegantly designed to share electrons. And so we are a carbon-based life form. They have talked about things that are silicone-based life forms potentially. All these theories have been around as far as we know, because the only life we're familiar with is life here is carbon-based, as far as we know. And that's because of the ability to form these very specific things that we'll get to today called non-polar covalent bonds. It's this interesting way of sharing the electrons. And that's something that's coming up very shortly. So this is really where we start the whole idea of chemical bonds. Really, it is an energy relationship. And sometimes it's relatively weak. Sometimes it's easy to break. Sometimes it's very difficult to break. So And really, when they talk about it, it's the amount of electrons and really how they're distributed in these various atoms as to how they get together, as you will see. And so this is the whole idea of the so-called octet rule, other than the first, quote, shell or orbital, which only has 2, that's hydrogen and helium. Everything else have 8. You'll see again, and I hate to keep flipping back and forth, but it's probably necessary. These guys here in yellow, they're called transition metals, zinc and nickel and cobalt. And you'll see titanium. You'll see different metals that are in there that you're already very, very familiar with. Understand that they behave a little bit differently. They have an extra orbital, and sometimes they can use 1, 2, 3 electrons. They're an oddball, and that's more of a chemistry course. Okay, and it's because of that why we're so careful, like in a microwave, putting metals in there in a microwave inadvertently, because those things will start flying around and cause fire. Because what happens is it makes electrons that are easy to move around super fast. That's why we use things that are not so easy to move around. So to me, that's more of a chemistry course than what our course is here, but I thought it would be important just to mention it. So again, there's a lot. They said there's up to 7. Understand that we basically start working with these shells of 8. We have 2, then 8, then 8. So if you add that up, 10, then 18, then 26, etc., etc. Depending on how they're distributed, we call that outermost shell the valence shell. And by definition, it's an important definition, the number of electrons that either have to be gained or lost to either complete or empty a shell is the valence number. If they only have 1, then you only have to lose 1. If you have 7, you only have to gain 1. They're totally different in their properties, but their valence number is 1. So it applies to either how many to lose or how many to gain to either empty or complete that shell. It's an important definition because the valence shell is where the chemical properties come from, period. That's what creates the periodic table, the similarities in those outer shells. Okay? So here they're talking about the 8, except for hydrogen and helium. It's the driving force. You can see they're eagerly seeking ways. Just me, please. Okay, to complete those. So the Nobel or inert elements or inert gases are all in whatever name they're using them. Again, that's more of a chemistry course. So atoms will gain or they will lose to achieve stability. So here are the chemically inert. They have completed valence shell. They're giving you helium rather, and neon. So I have to say about them. Now we look at ones that are not. Hydrogen, unique. Because you'll either lose 1 or it will share. That's the interesting thing. It doesn't necessarily gain 1. We don't see H with a minus sign at all. Okay, oxygen. And you see it's years ago, we used to have little pairs. So, and this may not be entirely accurate the way they depicted it there. My marker, which I forgot. The way I like to write it, because it's kind of the way we make water, is oxygen has 2 here. If you went into a 2-dimensionally, 2 here, and rather than having the way they depicted it there, it's more like 1 and 1. You'll see what happens when water is made. We're going to eventually see an oxygen with the 2 here, the 2 here. You have 1 here plus another 1 from a hydrogen. 1 here plus another 1 from a hydrogen, and now you have H2O. And it's that asymmetry, okay, the fact that it obviously is kind of loaded to one side. It's very significant. It's not like you might imagine from what they're showing you here. It's a hydrogen here and a hydrogen here. It's just not how it works. I can't go into the mechanism for a very good reason. I don't understand it completely, but typically, wrong word, exclusively, that's how we form water. And then you get to magic of carbon. This is why it's important to be able to think three-dimensional. Everything is on a flat surface like that. Understand, carbon has 4 bonds. So we're looking at them like a clock at 12 and 6 and 3 and 9. It's three-dimensional, it's spinning around. So those bonds are equal. They could be this way, they could be that way, that way. That's the three-dimensionality of it. Maybe you worked with those like little Tinker Toy models, the little stick and ball models. Those are really useful in understanding its ability to rotate and things like that. And you're going to see that we lose some of that rotation when we do what's called double and triple bonding. Because of that, it inherently alters the shape. So as we look at, and then lastly here, sodium, it's just like we saw lithium before. It has 1 electron all by its lonesome out here, 1 out of 8. It wants to lose that immediately, if not soon. So again, we don't see elemental sodium, and you wouldn't now find it in a science. I don't think we have it in our laboratory here because it's explosive, and your insurance company goes, no, we're not having that here. So these are the major bonds. You're going to see that there's a distinction in covalent bonds. We'll start with ionic. Ionic is very simple, opposites attract. It is strictly a magnetic attraction. It is not the sharing of the electrons. It basically occurs, and salt is the classic good old-fashioned sodium chloride is the classic example. Okay, you have something that has already ionized, sodium with a plus charge, and chlorine, which now is called chloride with a minus charge, and they attract to one another, positive to negative. It's universal, the attraction. So ion bonds don't really involve that. This whole nonsense, the transfer of the valence shell, baloney. It doesn't transfer anything. That transfer was accomplished long ago somewhere else. Long ago, the sodium gave up its electron, and the chlorine became chloride as it found an electron. It's not like I keep telling people the same thing. It's not like an explosive metal and poisonous gas looked at each other across the room, ran to each other, and made table salt. It just doesn't happen that way. But I realize they're trying to present it to you simplistically. When you see the word anion, it means a negative ion. If you see the word cation, it means positively charged. However you want to remember it, if you remember anion for a negative, the other one with the cat has got to be positive. To me, it's just easier to do it that way than any other way. Okay? And so this is what forms. Here we are. Here's that same illustration. It's like magically the sodium, oh, hi, chlorine, please take my electron. And chlorine's going, thanks, couldn't wait. Never happens. Here we are, sodium chloride. And all they are is there's no formal bond between them. And what's interesting was there's no strong bond or even somewhat strong bond between those electrons. There isn't whatsoever. It's easy for something that's compatible. It's compatible to get in between them. That's water. That's what water does. What happens when you put salt in water? It disappears. It ionizes into sodium plus and chloride negative. It ain't there no more. You can't see it unless you put so much in there you can magically see it because you do what's called supersaturating water. So by definition, we call ionic compounds salts. They're not just NaCl. They can be and again, if you get one of if you're like me and you want to get some kind of sea salt or some kind of gray salt or wherever you get it from, or Himalayan pink salt, what makes it interesting is all the different chemical components that are part of it. Okay, so whether it has sodium, it has potassium, it has iodines, chloride, it's fluoride. That's what gives it sort of the unique flavor that in general is salty. What happens when you eliminate the water? So if you take salt or if you take table salt, put some on a microscopic slide and take a look at it at sufficient magnification, it forms crystals. All salts make crystals. There's a whole science called crystallography of looking at those crystals. And indeed, that science is what gave us the structure of DNA. Well, that was in 1948. it actually was discovered. We'll get into that when we do the DNA part, and that's in the next section of this chapter. Okay, and those molecules, even though they're packed densely, because of the charge, water is tiny. Water can squeeze in between them. So it separates them immediately. Not all crystals are created equal. Traditional soil crystals are those nice, innocent-looking cubes. Have you ever heard of a disease called gout? Gout is from a crystal. It's called sodium urate. It's a more complicated crystal. It doesn't form those nice little cubes. It forms dagger-like spears that settle in joints and punch holes in them. And they're so big that white blood cells can't gobble them up. They just explode. That's why it becomes extraordinarily painful. So it's not just the crystal. And the crystal is a very generic term. They all have different things. So some speak, deceased former college, my old college lab partner, she got her PhD and studied crystallography. You know, specific chemicals were there. That's why I learned not to Google anybody. When Google first came out, and I hadn't heard from her in years, so I wonder what she's doing. I'm sure she's teaching someplace. Must have been like 2000, 2001. And I Googled her name. I didn't know her married name. I knew her maiden name. I figured she published under that. What's the first thing that came up? Her obituary. Yeah, I think she was probably 46. She died by ovarian cancer, I think. So, you know, treasured chemistry professor, former department chair, loses long battle, leaves husband and teenage daughter. Ugh. Don't Google anymore, Lou. Very sad about that. So, covalent bonds are involved with sharing. So the ionic bonds are done. It's a relatively weak bond. It's a magnetic attraction, positive to negative, easily separated if there's something that can squeeze in between them. Whereas, and so indeed, salts are many of different ones are dissolved in our bloodstream and in different fluids. Where covalent bonds share. You can share 2, 4, or 6. And it means the difference between single, double, and triple bonds. And if you use those neat little tinker toy things that I call them, you had the ones with the little springs together, you couldn't rotate them all around. You took away what we call a degree of freedom. So the structure became more fixed. So that when you have a double bond, it is harder to change its shape in certain ways. And triple bond is almost impossible. And it basically eliminates what we refer to as a degree of freedom. So, and this way, and I understand sometimes they're not there the whole time. You'll see that a little bit when we talk a little bit about what are called organic acids. Okay, so we have 2 types: polar, which is an unequal sharing, and non-polar, which is equal. And that's important. So, here's carbon. Carbon is the classic example. If you do organic chemistry, this is the first organic compound. Organic compounds are defined as compounds that have carbon to hydrogen and carbon to carbon bond. Not all things you say, if it contains carbon, it's organic. That is not 100% true, because what we probably have as much of as anything, CO2, carbon with 2 double bonds to oxygen, is not organic. So carbon to oxygen, in and of itself, is not organic. You can have it with them, but not by itself. So this is the first one. It's called methane. Natural gas is mostly methane. It's carbon with 4 hydrogens, singly bonded, and you can see it's all about symmetry. Just like I talk about those clouds of electrons, they're equally distributed. Because of that, anywhere here, I'm as likely to find an electron as any place else, whether it's side to side, front to back, up or down. They're spinning around that nucleus equally at any one point in time. That's what makes them non-polar. Polarity means an unequal distribution of charge, meaning one area may be a little more positive, another area may be a little more negative. Not the case here. The more you have of those, if you want to go with it for a bit, the more nonpolar it is. The more nonpolar bonds you have, the less likely it is to dissolve in water. You're getting to the crux of this discussion for now, which is water solubility versus fat solubility. Things that do not have, that have a lot of what are called non-polar covalent bonds. Okay, I'll be right. They have polar covalent bonds. I'll tell you what those four are. They're very, very specific. They're unequally shared. The more of those you have, the more likely it is to be water soluble, because it's just like water. When I do that water molecule up there, you're going to see shortly that is an unequal share. Very important. Because we're going to add a little wrinkle to the mix at the end. That's part of it. So these are all single bonds. That's what they're talking about, a single bond. These are by definition classic non-polar, equally distributed covalent bond. Post. Put another carbon, you have something called ethane. You put another carbon in, you have propane. My son's, that's what he was done for years. He's a CDL driver, and did bulk propane, did cylinders, hazmat license. So here you have oxygen. Now, oxygen gas is equally shared, except rather than doing it with just one, here's how you see how they did it this way before, but the reality is when oxygen and oxygen bond together, it kind of does this. That's why it's better to draw the oxygen this way with that +8 in the middle, and the two in the outer orbital, I do 2 dots here, 2 dots here, dot here, and dot here. Those guys kind of come closer together. And it's almost as though they have like 2 dots over here, and they bond with another oxygen that's +8. There's dots here, and 2 dots here, and voila, you have a double bond. So that's where O2 comes from. Very important formula. That's the way we find oxygen almost everywhere, and oxygen is such a big player when we get into the sort of what's happening with life and its role. Oxygen is there as a parking place for all those electrons. We're sucking the energy out. Because if we can't find a place to park them and get rid of them, we got a problem. Nitrogen, very similar on the periodic table, and I'll show you. So you look at the periodic table, oxygen and sulfur behave similarly. Nitrogen and phosphorus behave similarly. So, but nitrogen gas is something, 80% of what we breathe every time we take a breath is nitrogen gas. It's part of it's what our atmosphere, 80-20. And with some trace elements or trace gases that are in it. Okay. Nitrogen, on the other hand, is not a double bond, but it's a triple bond because of where it is in the periodic table. It has 3 unpaired electrons. So a convenient way for it, as you can see here, it has 1 pair of electrons, and then it has 3, and they've drawn them over here. It's not a great drawing. So you might have a pair here, and then a single here, and single here. And the 2 of them come together, and naturally they form this triple bond. That's where we find nitrogen a lot. Again, 80% of the air we breathe is nitrogen. So that's yet another bond that's there. That's a triple bond. Oxygen, O2, nitrogen, N2, hydrogen, H2. Those are all nonpolar covalent by definition, equal sharing. So equal sharing results in electrically balanced non-polar, and carbon dioxide is the same way that I had written before. You have, just to reiterate, carbon has 4 electrons in the outermost orbital. In this case, we get 2 pulled to one side, 2 to the other side. Oxygen has its 2. So you have C, double bonded O, double bonded O. Down the road, you're going to see the carbon dioxide. Carbon dioxide dissolves in our bloodstream. It becomes really important down the road because it balances our pH. Carbon dioxide mixes with ammonia and makes something called urea, which is a lot less toxic. It's fascinating. We get a lot of extra use out of these very common biological, and they're not, in these cases, these are inorganic. Yet they have a lot of uses. So here we are, electrically balanced, non-polar molecule, carbon dioxide is one of them. Here it is, C double bond O. So the way I always would frame it is unequal sharing. They would have failed kindergarten. You know the whole thing about kindergarten sharing? No one told my kids that. We are now into the third week of kindergarten for my grandson. We are amazed that he is still being allowed to come and that the teacher has not resigned. He is a bandit. He's a very lovable bandit, but he's a bandit. Over the summer, I was showing him how to use the microscope and do oil immersion. He's one of those 5-year-olds. Don't ask me. No genetic ties. All my kids are adopted. Just one came out of the woodwork. Unequal sharing of electrons, okay, results in electrically polar, meaning there's an imbalance of charge. Different electron attracting abilities. We have electronegative and electropositive. H2O is a polar molecule. I'm going to show you everything. That's why I'm kind of going through this. I never refer to it as a dipole, but oxygen, I'll show you what it means by being more electronegative. It's the whole foundation of unequal sharing. Water and oxygen, total failure in kindergarten. Here it comes. Here's good old H2O. You get the oxygen here. Okay, we get a couple here and a couple here, a couple here. Just for argument's sake, we'll put one here, one here. I'm glad I put different colors today. That's really making my job a little easier. And I'll put hydrogen here. That's water. So it's created a share arrangement, oxygen and hydrogen with a couple of single bonds. The problem is this. Oxygen has a charge of +8. These are each +1. The electrons are being pulled more toward the oxygen. We call that electronegativity. It's pulling the electrons to them. When we look at, so all those electrons are going this way. Now, you might say, but wait, why doesn't it happen to carbon? Carbon is +6, and you have hydrogens and methane equally distributed around them. And they're only each +1. The difference is they're equally distributed. They're symmetric. That is a symmetric molecule. This is asymmetrical. The asymmetry is the critical piece. So what happens here is we're basically pulling them closer. We're actually having an electron tug of war, and the oxygen is winning. So what happens, to draw away from my terrible artwork, now the oxygen has pulled its electron, since I just changed the color, I'll make the blue ones now. They pulled those a whole lot closer so that the hydrogen here and the hydrogen here should be that blue. I got to color coordinate better. Effectively, they pulled it so this, the oxygen part of water, is now, and this is the side. The Greek letter delta looks like that. That's like capital letters. When we do small letters, it looks a little bit like this. Delta, so this is partially negative, and if you look at this molecule as sort of like this, it makes the oxygen side partially negative and the hydrogen side partially positive. So effectively, you have an unequal distribution of charge, which makes it a polar molecule. And you will see that the more of those OHs, if it has OHs, because they're very similar, NHs, PHs, and SHs, any of those bonds are going to have a tendency to form polar covalent bonds. And inherently, that's going to make anything that has more of those it has, the more water soluble it is. Because water is a polar molecule, and this makes other molecules with those polar as well. Some things have a mixture. Like alcohol, technically is water soluble, but you also get some solubility in fat or lipids. A little bit of both. That's better artwork than mine. So you can see the red side is the oxygen side. There's that script letter delta, negative. It's not like, fraternities and sororities where you use the formal letters. Okay. And here, partially positive. And so, and that's where we get that V shape, and we can measure that. Using, sophisticated measuring devices, you actually can calculate the angle. It's not 90 degrees. Since these areas are both positive, they repel each other. So rather than being at 90, it's like around 106. You don't have to know, but it gives you an idea that this is a real thing. Unequal distribution of charge. Okay. So like if we change this in some of the health science majors are going to be taking chemistry, that's something they may or may not. I don't know. Like I said, I was a chemistry. I got my chemistry degree 52 years ago. It was still chemistry then. So ionic bonds, it's not the idea of transfer. I like the fact that it's ions and it's just a magnetic attraction. Here's the polar covalent, unbalanced charge, asymmetric, unequal sharing versus non-polar, equal sharing. But we're not done yet. And this brings us to the magical powers of water. Why water is so unique a molecule in our body. Hydrogen bonds. Hydrogen bonds are the weakest of all the bonds. They are a slight magnetic attraction. If one isolated water molecule has one area that's positive, negative, and one's positive, when you have a bunch of water molecules, they are going to interact with some degree of a magnetic attraction. I'll let the diagram speak. So the attraction between electropositive hydrogen on one and electronegative portion of the atom, okay, of the oxygen part on the other. It's not a true bond, but it accounts for remarkable things about water. So you can do this. I don't recommend you doing this experiment at home, unless you have regard for your fingers. If you have two identical pots, saucepans, they have to be coated, and you put any kind of cooking oil, whatever you want to put. You want to be cheap, vegetable oil, canola oil. We use avocado oil, high smoke point. And you put water in the other. You put equal volumes. 2-quart saucepan, put a quart of oil and a quart of water. You have two burners that heat up equally, crank them up to high. Stick fingers in. Which one are you going to pull out first, the water or the oil? Pardon? I didn't hear you. I didn't hear you.
The oil.
Thank you. My wife says that. I can't hear. And my ears are clogged right now because it's allergies. The oil. Why is that? You got it right. You're already ahead of the game.
I was thinking like when you deep fry something almost, like it gets really hot.
Really fast.
Really fast.
Okay, because oil, all those molecules are identical. They're not bonded together. They're just held together because oil likes to hang out with oil. Okay, and so all that heat, average kinetic energy, making them move, immediately they start to move faster. Water takes time. And why do we cook with avocado oil? It's got what's called the smoke point when it starts to break down. Avocado oil is about 450 to 500 Fahrenheit. If you're using EVOO, extra virgin olive oil, first called fresh organic, might I add, it's going to start to break down 350 to 375. That's why you don't want to get burnt oil as not a flavor you want to be associated with. Okay, where water, we'll talk in metric 100 degrees Celsius, or we talk 212 degrees Fahrenheit. As hot as it's going to get, and it takes a while to get there because you have to break down these hydrogen bonds. That's a very important. Water is forgiving. We're 75 to 80% of water. That's why we can stand homeostasis. Big changes in temperature, whether it's 100 degrees outside or whether it's, we have the ability. So our bloodstream is not going to freeze up and it's not going to boil over unless we're in an extraordinary extreme for a particular length of time and we don't have anything to protect us. Just like that. I mean, I for whatever reason, my wife and I, we used to go to Palm Springs, where it's already 100 degrees, 110 degrees in the shade in summer. Okay, but it's a dry heat, you know, I'll walk around and that stuff. Like everybody's got different things because it's very much different. Okay? So, I mean, there's different ways that the heat affects you, but still internally, pretty good. Actually, it's a lot more fun when you go someplace like a beach where it's not going to be ridiculously hot like that. But we digress. So an attractive force, a weak magnetic attraction between, and these are called dipoles, fancy name, which makes water a liquid. Okay, intramolecular bonds. It's better to see it. I don't know if you're gonna have sound with this or not, but I'm not worried about it. It kind of shows you. I don't have the sound up. I think. Tell me it's playing. Oh, it is.
Closer to the oxygen. Because of this unequal sharing of electrons, the oxygen atom in the water molecule actually has a slight negative charge, and each hydrogen atom has a slight positive charge, even though the water molecule as a whole is neutral. Because of the unequal sharing of electrons and the resulting positive and negative poles, a water molecule is said to be polar. The polarity of water molecules causes them to be attracted to each other. Since the positively charged atom involved in this special type of attraction is always a hydrogen atom, this kind of bond between molecules is called a hydrogen bond.
Here. And they're super important.
Each molecule can hydrogen bond to 4 other water molecules. A hydrogen bond is weak and lasts only a tiny fraction of a second, but it takes a lot of energy to overcome the combined attraction of many hydrogen bonds. This explains water's great capacity to store heat, its high boiling point, surface tension, and several other unusual properties.
That's the mystery of water. Okay, so you have that extra. Why does the oil heat up faster? Because the first part that he has to do is break those bonds, and it takes some additional energy just to get started to move the individual water molecules around. What happens when water freezes? Okay, those bonds elongate and then firm up. So the density of the water molecules is not as dense as the liquid. So it's ice, and it goes to the top of the surface. When the river freezes, the ice doesn't form at the bottom, it forms up top. Okay? Even though there's sunlight hitting it, but the nature of water is such that the ice is less dense, and so we begin to first form slush ice, and then finally it ices over if it's cold enough for a long enough period of time. And around here, when all that ice breaks, we can get some pretty serious flooding that goes on, and you have to be watching. And a lot of steps have been taken over the years by the Corps of Engineers, the Army Corps of Engineers, to stop that. And that animation talked, and that's why I like the animation. Talked a little bit about those properties. Surface tension. Water molecules stick together. Has it ever happened to you where you put water, let's say in a Pyrex, container, and you measured it for a recipe in the microwave, and when it came, you put it in for 3 minutes, and when you pulled it out, all of a sudden it splattered over and you got burnt? Water superheats. Okay, what professional chefs do, they put a glass rod in there. It breaks the surface tension. So and that's what professional chefs do. That way, it's superheating those molecules. It's making them move faster. They're not all magically going to stop 212. A lot of times, you have to have a way to sort of dissipate that surface tension. It's very interesting if you look at that stuff. So here it is up close and personal. And it's not just one. Each one of these will do the same thing with another 3 different molecules, and so on and so on. So when you have all of that tiny bit of magnetic attraction we call hydrogen bond, multiplied by all those untold billions and trillions of molecules are tiny. You get back to 6.02 times 10 to the 23rd. They make tension. And so you'll see, inevitably, I show you a picture of a bug called the water strider. And basically, there's not much to the bug, but it has evenly distributed the way it's standing on the water. So if we see this in nature, it's not enough to break that surface tension when its weight is evenly distributed. Where you and I would break it pretty easily just by going in there. We might be able to float if we have that capability. Aha, water strider. So that's kind of the part. You're going to see down the road that those properties like surface tension, the fact that water pulls water along. It's like when you can take water and it's like taking your finger on a straw and you can be able to pull stuff up. All of those neat things are really part of what we call the colligative properties of water. It's a fancy name physiologically, and that's really the sort of the hallmark of homeostasis. What makes homeostasis work? Water. It's very forgiving if you heat it or you cool it. It has other neat stuff that it does. It holds things together, but it can be pulled apart with a sufficient amount of energy. It's the beauty of water. This is chemistry. Okay. See, they talk about reactants and products. But living reactions go both ways. First thing you have to learn if you're talking about anatomy and physiology is we don't have one-way traffic. We make things and we break things. They go until the idea of reactants and products is somewhat archaic. It really is not, to me, modern thinking. It's like if you heard about anatomy and physiology, they talk about with muscles, origins and insertions. Really, the modern anatomist talks about attachments. Because, I mean, the question is, if I'm stepping on the gas, then you have an origin and insertion. But if I'm standing up my toes to reach something, it's going backwards. If you're stepping on the gas, then the fixed part is your leg and your foot's moving. But if you're going up to reach something, now your foot's the steady part and your calf muscle is allowing your leg to move. So you have to look at it from a sports, which I did a lot of. Those kind of things, a lot of sports medicine, you have to look at it that way. I know it's the perfect time of year to study it. Yeah, nothing like early in the season, late in the season, early in the season, because the athletes, despite all the conditioning, this is where we see injuries, specific injuries. So, I don't make a big deal. You can put things together, making something. We're creating a bond between A and B, storing energy. So that's anabolic. Like anabolic steroids. We're storing energy. We're building something. So we can take, this is making a protein. Individual components can be called amino acids. They don't all have to be the same. There's 20 of them. So we have an unlimited amount of proteins we can make. Proteins have to do with how many we chain together. You have to have at least 100 to make a protein. Anything less than that, you will learn, is called a polypeptide. We'll get to that in the next thing. And we can break something apart. This releases energy. Okay, so here, bond breaking. They already have it passed backwards in this PowerPoint. But you have the arrow pointing in the other direction. If we take what we made, A and B, together and break them apart, now we're going to release that energy that we stored. So immediately this is a PowerPoint error. You always see. And so here's what we do. The way we store sugars, and we have a very limited capability to store sugars, is what's called complex carbohydrates. Long chains of sugars is glycogen. We only have 2 places where we store it, liver and skeletal muscle, period. Nowhere else. When we break it apart, we release glucose. In an emergency, our body sends a signal to the liver where the glycogen is, one area, and says, we need extra energy. convert the glycogen. It's called glycogenolysis, break a lysis to break it apart and release glucose. There's a hormone that's released from your pancreas called not insulin, that works differently, but glucagon. And that does that. And so that's how you're breaking it down. You're releasing energy, but that glucose is eventually going to be used to provide energy for a variety of reactions. And yeah, we can flip things. We can put C in here for B. We could flip D and B together. That's great exchange or displacement. I never called it that. Who cares? This is a biggie. When we get to it, the single most common reaction in our body, whatever you weigh like me, 195, 200 pounds, I'm sporting. If you weigh, like my sister does, 97 pounds soaking wet, she'll be 80 next month. She weighs the same as she did in college. She and her husband both. He weighs 100. Hate that. But I digress. You make that much ATP and you break down that ATP. We continuously do that. Okay? As much as you weigh, that's how much you do during the day. If you add up all the ATP you either break down or assemble, you come up molecularly and weighted with as much as you weigh. Because we're constantly building it up. It's just an endless cycle. It's the most interesting molecule, I think, the most unique molecule we have, because they're called high energy phosphates. And we'll look at those when we look at nucleotides. That's a nucleotide that we use all the time. It's called adenosine triphosphate. It's called adenine. That's one of the genetic part of the genetic code. That's a sugar. Okay. And then we have 3 phosphates, hence the triphosphate. And so, don't even worry about it. I was not going to ask you about redox reaction. I was a chemistry major. We hated them. Nobody likes them. It's very counterintuitive. You see, when something oxidizes, it loses electrons. When something reduces, it gains electrons. Basically, when we reduce by gaining electrons, think of reducing the charge because it's a negative electron. So you're making it smaller, if you want to think of it that way. I just remember when we oxidize something, we lose electrons, and reduction is the opposite of that. It's one of those, basically, just because rules, just because I said so. I don't go out of my way to remember it. I probably won't ask you about it, because I hated them in chemistry. I like stoichiometry, balancing and stuff like that. And so we basically can classify all the reaction as they release energy. We used to talk about heat, so we had exothermic and endothermic. Now, because there's more than just heat, we call gonic. I didn't make that up, but it's the way it is. When I was in school, we didn't have domains. The domain theory, we're part of a eukaryotic domain and stuff like that. They came out in 1978. I got my doctorate in 77. So we had kingdoms, good old kingdoms. So exergonic, okay, what that means is we released energy. Endergonic means we stored it. We made bonds, we broke apart bonds. It's all it means. And typically when we break bonds, we have to use water and oxygen. So that's where the oxidative comes from. And then the idea, and that's why I hate it when they draw arrows. They're not all equally reversible. We don't have as easy to go from forward to backward or backward to forward. That's why I don't like reactants and products, but they're effectively all reversible to some extent. You're going to see it, and I'll point out the ones that are not. Okay. So we see some, it's like if you're cooking a steak or an egg, you can't reverse it. You're doing something in there called denaturing proteins. You can't go to a restaurant and come back and they bring out the steak and go, I'd like it more rare, please. Sorry. Now, if it's rare and you want it better done, we can help you with that. Okay. So that's what I mean by reverted. You'll see that in medicine, the words reversible is a very good word. Irreversible is a very big word. Treatable is a good word. Curable is less common. Treatable is a good word. You learn those things as time goes on. You can't necessarily cure things, but if you can treat them, you're not doing too bad. And again, temperature, big player in all this, increases the speed. And it's just when you talk about concentration, they use the term reactants. I think ingredients, typically you have more of the ingredients, you can make more of the reaction or make it faster. And smaller things go faster than bigger things. Like electrons are a whole lot faster moving around than protons. Just think of it that way. Those are sort of general ideas. In general, faster and smaller makes faster, temperature makes faster. And faster is important. And you're going to see that a lot of when we talk about enzymes, the catalyst is something that's neither consumed or destroyed. Something that's reusable literally thousands of times a second. So a tiny bit of catalyst can make a lot of a reaction go very quickly. And you'll see that they're so terribly important. When you hear about genetic disorders, whether it's cystic fibrosis, certain kinds of muscular dystrophy, hemoglobinemia is like oh, I hate reference, right? The name escapes me. It's Crown Heads of Europe, factor VIII deficiency. That's coming there, but we'll get there. But there's all of these are genetically based. Typically, it means we're missing a catalyst. All of those reactions, whether it's simple as oxygen and hydrogen coming together and making water, typically involve a chemical called a catalyst, which is really, compared to the size of the reaction, a giant protein that allows that to happen. And so we'll take a look at those just to give you a heads up, and we're going to stop because my voice is going to die. Oh, it's going to die. Kind of like going forward stuff. Let's see if I can help you with it. Come on. You look through this thing, the next thing we're going to start is really the biochemistry. We're going to look more specifically at what water does, the concept of pH, which is very important. We're going to look then at the different carbohydrates, simple and complex, the variety of different fats, and there's more than one type. The family name is called lipids. Fats are lipids at room temperature because they're solid. Oils, like avocado oil or canola oil, are liquid at room temperature. They're both lipids, and we kind of generically call them fats. But from a definitional standpoint, fats, like my favorite personal fat, butter, is solid at room temperature. Food moment for butter. And proteins, what they're made of, and amino acids and nucleic acids and nucleotides, all of that. So we're going to look at all of those things that are part of it. So I'll leave you with that. Thank you for putting up with me for all this time. I see Dr. Robbins is finally letting out his captives. They all look overwhelmed. Have a wonderful rest of your day, and thank you.